Begin. Okay. Um, we started to discuss multivariable calculus talking about functions of more than one variable. And on Sunday we talked about limits of such functions. And today I want to talk about derivatives of such functions. It will take probably more than one lecture, which is okay. We'll continue it in our next lecture. And I start with, if you do study probability this semester, you probably have already saw it, the concept of partial derivatives. Am I right?
Yeah.
A function of for example, a function of two variables, f, x, y. So you can find derivative by using x, using y, or not?
When?
Probability.
Uh, yeah.
Not yet? Okay. No, yet, not yet. Um, Partial derivatives. Let f I don't know, from Rn to R be a function. We can discuss the partial derivatives. I mean, derivatives, not the whole derivative or a one derivative for all variables. We can discuss derivative for every variable. For every variable, I don't know, xi, we can define the partial derivative and of s by xi, denoted by, I used to denote it fxi, something like that. Xi is in the index. Um, or you can add the tag if you want, something like that. Or if you like the notation df dx for one variable, you can use the snail f, snail if something. I don't know what the actual name of that thing inside. And probably there are a lot of more notation. The derivative is something very basic. And before we look at the very definition of partial derivative, I want to tell you how do we actually do it using the rules of differentiability we already know from function of one variable. Before the definition itself, before we present the definition itself, we explain how to actually compute these partial derivatives. When we differentiate by xi, we think of all the other variables as constant. We consider all the other variables to be constants, and we differentiate by this way. Let's do some examples. Let's begin with fxy is a function x to the third plus y squared plus 3xy plus y, for example. So when we find the partial derivative of f by x, we consider y to be a constant. So the derivative of x cubed is 3x squared. The derivative of y squared is just 0 because we consider it to be a constant. So Derivative of a constant is 0. Now, the derivative of 3xy, we consider y to be a constant. So it's something like 3y, like 15 or something, multiplied by x. We are left with 3y. And yet again, the derivative of y is 0. Of course, we don't have to write down plus 0. We could take 3 to be like a common factor or something, but I just want to show you how to compute the derivative. So arranging them nicely is not very important to me. And on the other hand, if I want to calculate the derivative of f by y, I'm considering x to be a constant. So the derivative of x third is just 0. Derivative of y squared is 2y. And 3x multiplied by y is just like 5 multiplied by y. We're left with 5. We're left with 3x. And the derivative of y is 1. So we differentiate using our rules from functions of one variable. The derivatives of polynomials, of exponentials are all the same. And we consider the other variables to be constant when we differentiate by some variable xi. We will see the definition of partial derivative using limits and stuff. In our lecture, and then we can understand why we consider the others to be constant. But right now, I want to write down more examples for the computing itself, finding the derivative itself. Let's go for one more tricky, but not very tricky. Example, y multiplied by cosinus of xy. That's good enough. Or let's see. Let me consider the means. So when we calculate the derivative by x, we consider y to be a constant. So the constant stays the same. We don't touch it, and we differentiate cosinus sinus, it becomes a cosinus, and moreover, we need to multiply by what's called in Hebrew the inner derivative, the derivative of the function inside. So write down explicitly like that. We still need to differentiate x multiplied by y by x. This is the right place to say that when you have to calculate derivatives in the final exam, finding extrema or something like that, just write them down without any steps. It's good for you, writing down steps, so you won't get confused. Derivative of x by y multiplied by y by x. You can write it down that way or that way. It doesn't matter. Is just y, so it is y cosinus xy multiplied by y. Yet again, it's like we're 5x, so we're left with 5. So yx, we're left with y. You consider y to be a constant. 5 is my favorite example for a constant. Don't know why. Everyone can choose his own number. Now, what happens when we try to differentiate fxy by y? Suddenly, the y is alive. It's not a constant. It's a variable now. So we discuss a derivative of a multiplication. Yeah, for product. It's the derivative of y by y multiplied by the sinus and y multiplied by the derivative by y of the sinus. Now, sometimes I write the variable and then do the derivative. Sometimes I should start to. So y by y is just 1. And sinus by y is yet again cosinus multiplied by the inner derivative. And here, the inner derivative by y is x. It is not y. So one bit more tricky, bit more interesting example. Here, changing our point of view from x to y changes the way we look at the function. It's not a scalar anymore. It's a product, it's a multiplication. And we differentiate the way it needs to be. You know what? Let's look for another example. Something even more when the difference between x and y is even more emphasized. Fxy is x to the power of y. When we think of x as the variable and y as the constant, it's just a polynomial, x to the power of 5. So y jumps out in Hebrew, x, y minus 1. And on the other hand, when you differentiate by y, consider x to be the constant, is the 5 to the power of y, it's exponential, exactly. And how do we differentiate an exponential? The exponential stays the same, and correct, we are multiplying it by the logarithm of the base, which is ln x. And for our my next trick, last example before we talk about the definition. As I mentioned on Sunday, most of our examples are of two variables. Most are of two or three, but from time to time we do mention an example of more than three variables, which is totally fine. F from Rn to R, that works the following way. F of x, and here x is a vector with n coordinates, is the norm of x. Basically, yes, f of x1 to xn is the square root of the sum of the variables squared. So if I want to find the derivative of f by sum xi, and even though, or first look it looks complicated, but on the second look it's actually even easier or shorter than the first examples because it's the same for every xi. Don't have to calculate differently. As I told you before, I'm already a grown up. I have a PhD. I fathered more than one child. My knees hurt. All the conditions. Yes, my old wound from the war. It hurts when the wind blows. And I never differentiate nor integrate roots as they are. I write them down with some fraction as the power, and then it's easier to calculate the derivative. Now my derivative by xi. So the half jumped out, as we say in Hebrew, and it is the power of minus half. And of course, we need to multiply it by the inner derivative, which is the derivative of the sum by xi. But even though the sum is frightening, even though the sum has the three or say four dots inside, oh, the x squared are just getting canceled. They're just zero. They're constant by the eyes of xi. And the derivative of xi squared is 2xi. So it is half and 2xi. Of course, one can, it's not very important, one can rearrange it, look better. This is the norm, but it is in the denominator because it's minus half and not half. The 2.5 cancel each other, so we are left with xi over the norm of x. And I want to write it in a different color because it is really not important to the derivative itself. Let's choose to. Okay, so by the rules of derivatives, it's pretty easy, or at least not requiring much thinking, calculating, computing, finding the partial derivatives. What is the definition of partial derivatives? Sammy, any questions? Sammy, you here? Sammy or Lev? Who is it? Sammy.
No, I'm good.
Okay. So, what is definition? How do we define fxi? So remember, as I said in our last lecture, the best way to grasp the definitions and whatever we're doing is to compare it to the same things of in one functions about functions of one variable. And how do we define the derivatives for a function of one variable? For f of one variable, we define the derivative at some point a as the limit where age goes to 0, fx ועוד fa ועוד age, minus fa above age, and one can think of it as x goes to a, fx minus fa above x minus f. Equivalent definitions for the derivative. Now, we do the same for the partial derivative fxi. We add age to the I coordinate. We know how to denote it mathematically. We denote EI, the vector of one in or at the I, coordinate, and 0 in the rest. In all the other coordinates. And so the derivative of f flag a, which is now a point of Rn, a vector, is the limit where age goes to 0 of a plus age multiplied by ei in order to add this age only in the I coordinate. For example, if f is a function of three variables, x, y, z, then the derivative of f by x at some point ABC is the limit of a plus h bc minus f abc. We add the h in the first coordinate corresponding to x. And we can say the same for f by y. We add the little h to the second coordinate. And same goes for fz. We add the little h to the third coordinate. And when do we use? Yeah, it's my bad. You are extremely correct. And generally speaking, we add the h to the specific coordinate and nothing more. We denote it in vector language age multiplied by ai. First of all, we can see from here, at least intuitively, that when we differentiate by some variable, the others are constant because we do not touch them, stay the same. For example, we differentiate by x, so we do not touch y and z here. And secondly, just like one variable functions, we know that when we can use our rules, x squared is 2x, etc., we use them. When we have no other choice but using the definition in order to find the derivatives or one variable function or partial derivatives of multi-variable function, when we encounter a piecewise function, we want to calculate its derivatives and partial derivatives at the very point it splits, or whatever you say it. And we can add something here that wasn't, it was in Infi 1, but it's talking more elaborate here. When we want to find the the partial derivatives of a piecewise function. At the point where it splits, we have to use the definition. Furthermore, or in addition, we need to use the definition when we encounter roots at the points that zero them. Let's write two examples. Then we explain what I mean zero them and so on. Example A. That word right now. 1, 2, 3, 4. And it can be 1, 2, 3, 4. Again. The function fxy is the following. Function will be seen on Sunday, x multiplied by y above x squared plus y squared, wherever x and y are not 0, and let it be 0, where x and y are 0. Space it out a little bit. Okay, so by definition, the derivative of f by x at 0, 0 is the limit of some little h goes to 0. F of f 0 plus h 0 psi 0 minus f 0, 0 above h. Now, specifically here, it's pretty easy to calculate them. F0, 0 is 0. And 0 plus ag because edge. Minus 0, I don't have to write down. And fh0 is putting here age instead of x and 0 instead of y. Oh my god, didn't copy it correctly. Could be better now. Age instead of x and 0 instead of y. What are we left with? It's only 0 in the numerator, so the limit is 0 itself. And one can easily see that similarly, the derivative of f by y at the origin is 0 as well. What they want you to note here before we continue, for the second example, note this function is not continuous. In lecture number 20, which was, of course, fun, we saw that the limit of this function where xy goes to 0, 0 does not exist. However, the partial derivatives exist. From infi1, we know that differentiability is stronger than continuity. Every differentiable function is continuous. So the question is, what is actually a differentiable function of more than one variable? Having existing partial derivatives is probably not enough. Moreover, write down as A and B maybe.
You differentiate by one of the variables, then you differentiate by the other variable, and those results are completely different.
Yes.
No connect. I mean, there's a connection, but like, no, we don't.
No.
Then we don't do anything.
No. That's what I want. It's exactly what I want right here. In this specific case, in this specific example, we got that the derivatives, the partial derivatives at 0 are the same. It is not always true. And moreover, even if it is true, it doesn't say as much about the function. And when it is true, it does not say much about it. So in this specific case, probably in other cases, but there isn't any connection between fx and fy. I mean, for first kind of examples, we got totally different derivatives for x and y. Okay, for my second example, let's consider some square roots. And it will be 0 as well, so it's probably boring, but it's a good example. We'll use it later on. Let's say the fifth root of x cubed y squared. I mean, why should we use the definition when it comes to roots where the point is zeroing the root? Because if I try to find derivative using the rules, okay, in a different color. Using the rules, let's say I want to find derivative by x. So as usual, I write it down with 1/5 in the power. I want to find derivative of that by x. So the 5 jumps out, whatever you call it, and becomes minus four about 5, and it is multiplied by the inner derivative by x. The inner derivatives is 3x squared y squared. Okay, we know how to write it down using the basic rules of powers. On one hand, we have 3/5, excuse me. Sorry. And on the other hand, it is x squared y squared above the fifth square root of x3 to the power of 4, which is x12, whatever, and y8. Hopefully I'm not wrong. Is that so? Now, we do have x to the power of 2 here, which is x to the power of 10 inside the root. So we are left with x squared in the denominator. And of course, the y, on the other hand, can be taken care of as well. Now we cannot put x and y to be 0. The denominator is zeroing. So we cannot get fx 0, 0 from putting 0, 0 in fx, because the denominator is zeroing. However, as I mentioned before, when it comes to roots at points that zero them, we need to look at the definition. I mean, on the other hand, it doesn't mean that fx is not differentiable at 0, 0. It means we need to use the definition. So by definition, as I mentioned before, we will see shortly that just like the previous example, we get here 0 as well. It is not necessarily so. As I mentioned before, sometimes one derivative is 0, the other one is pi, or whatever numbers you like. Sometimes one derivative exists and the other doesn't. It's all on the grill, as we say in Hebrew. All can be. Here it is the square root, no, the square, the fifth root of edge multiplied by 0, which is yet again 0, so it is 0 all the way up. And fy00 is the same as well. And again, it's not always 0, etc., etc. But here in the two specific examples, that's what we got. So this is the definition of partial derivatives. Any questions about that? Okay. Okay, so before we move on to try and understand what actual differentiability means here in more than one variable, I want to talk about high order derivatives. Um, let f be a function of Control S of two variables fx y. We can differentiate f by x and then differentiate f by y. When it comes to one variable, we can just differentiate by the same variable over and over again. Here we have the choosing of which variable we want to differentiate by. Yet again, what do we use differentiate for? Why will I want to differentiate by x and then by y, or by y and then by x? We'll see next week, mainly talking about extrema, but we will mention Taylor series of modern variable. It will be extremely fun. We have four partial derivatives of order 2. We have fxx, which is the derivative of fx by x. And the same goes for fxy, fyx, and fyy. And generally speaking, and in general, we can differentiate by xi and then by xj and then by xk, and so on. No matter how many variables do we have, no matter how many times we want to differentiate, of course, the function, the partial derivatives should exist, which is not always the case. The limit doesn't always exist, of course. But considering our elementary functions, they do have as much derivatives as you like. A combinatorial question is how many derivatives there are. I mean, generally speaking, a function of n variables, how many derivatives, partial derivatives of order k there are.
Okay.
Yes, you still need from the n variables, choose k variables to differentiate by. The choosing is you can't choose the same option over and over again. And the question is, does the order of differentiating matters? So let's go for an example, and then we'll state my theory about it. Yeah.
What I don't get here, and probably in the example, is what do we do after first differentiating? Because at the start we said it's just we treat them as a constant, the variables we are not looking at right now, and then we can select which of the two are, or which of the variables is going to be constant.
So can select is a tricky phrasing, because when we next week we'll see how do we use the second order derivatives. It's not about can or able, it's about what we have to do. But if we are expected to calculate fxy, how do we actually do it? That's what I want to talk about right now. And for example, let's look at the function from one of the examples earlier. For example, xy, semicolon. We have already seen that fx is y x y minus 1, and fy is xy multiplied by ln x. Now, if I want to calculate fxx, I need to differentiate by x the derivative by x, which is y x to the power of y minus 1. Yet again, when we differentiate it by x, we consider y to be a constant. It's just a polynomial, so the y minus 1 jumps out, and we are left with x to the power of y minus 2. Very nice. And the same goes for fyy. We differentiate fy by y, which is x to the power of y ln x, differentiated by y. Yet again, all the x's are considered constant right now. So another ln x jumps out, because that's how we differentiate an exponential function. Now, for the interesting part, say I want to calculate fxy, which is the derivative by y of the derivative by x. We need to differentiate by y the function y xy minus 1. So here we are being a bit cautious. First of all, I think it's easier to consider the minus 1 here as multiplication by 1 above x, which is totally fine. And now we differentiate by y. So the 1 above x is just a constant, stays outside. And here we talk about a derivative of a multiplication product. So write down slowly. Is derivative of y multiplied by xy plus y multiplied by the derivative of xy, which is 1. And this is xy ln x. And here I want to organize it so it will be easier to notice my corollary. I can take out x, y, and stay with x, y, ln x here. And of course, one can write it down as x to the power of y minus 1 by the rules of powers. It's a bit long, this line. It will be fine. It's my problem. On the other hand, if I want to calculate fyx, which is the derivative of fy by x, we need to differentiate by x to the power of y ln x, and it's all over again derivative of multiplication, the derivative of xy by x multiplied by ln x plus the x to the power of y multiplied by the derivative of ln x by x, the derivative of we actually don't need the parentheses here, right? Not multiply by anything. The derivative of x to the power of y is y x to the power of y minus 1 ln x plus x to the power of y. The derivative of ln x is 1 above x. Using the basic rule of powers, it is x to the power of y minus 1. And we can take x to the power of y minus 1 outside. And we are left with what? No, something's fishy. Y ln x. What something is. No, it's my bad here. It's not xy, it's y. Take out xy outside, we're left with the y here. And we are left with the same here. Y ln x plus 1. So the noticing will continue. fxy and fyx are the same. We got the same derivative, different ways, but we got the same. Notice that fxy and fyx are basically same function. The question is very clear. Yeah. The question is what the answer is. Is it always true? Now one can ask it in even more general form. Is the order of differentiating matters, or only the how many times we differentiated by every variable? Not just for x, y, and yx. I mean, x, x, y, y, or x, y, x, y. Is it the same?
No.
Let me introduce you to the theorem. I call it Schwartz, like the Cauchy-Schwarz one. He's a dead guy, like all of them. But probably you can call it about some other dudes. A theorem Schwartz. If the derivatives are continuous, then the order of differentiating does not matter. Only the number of times differentiate by each variable. In considering our elementary functions, miss the E here. All of their, that's right there or like that? No. Yeah, like that. All of their derivatives are continuous. All of them, just we've already seen it, derivatives of roots. Yeah. Only the derivatives of roots can cause problems at the points that's 0 the root. So basically we can say that we can change the order of differentiating and get the same result. Okay, for example, if the function, the derivatives are continuous, then derivative f x x y x, y y x, z y z, whatever, is the same as far as I can calculate counting it correctly, x x x x, y y y y, z z. The order does not matter. What matters is the number of times we differentiate by each variable. Now the combinatorial question changes, but the basic are the same. The basics are the same. How many different derivatives there are? Let's say a function with n variables. How many different derivatives of k order there are?
And k over k factorial. No. Depending on which ones you choose.
We're choosing the variables, the k variables from our n variables to differentiate by. So it's choosing, you can choose the same variable over and over again, but the order does not matter.
So I mean, you have the different xi, so it's n to the power of k over a xi factorial for xi factorial for every.
No, it's n plus k minus 1 factorial over k factorial n minus 1 factorial. It's choosing k from n with the option to choose the same option and without order. The order doesn't matter. But it's not a combinatorial question. It's just a nice question you can ask yourself. Yourselves. Okay. We'll see on next week that it is important. I mean, we're going to use matrices of the second order derivatives, and it's really important that fxy is fyx and so on. But now we can talk about the general case. The general case states that, at least by my how I put it, if the derivatives are continuous, then yes, they are the same. So a nice example, in order to find an example for fxy is not fyx, we need to go to the piecewise kingdom. That's just not necessarily, okay? But an example in which the fxy and fyx are not the same, you can use this function. See, I'm missing here the parentheses. And if multiplied by x squared minus y squared, one can check that the derivative xy at 0, 0 is 1, but the derivative of yx is 0, 0 is minus 1. I'm doing it without any explanation. I don't want to waste our precious time on this example, but I think it's good it is written here. You know what? It's not always fxy and fyx. Sometimes it doesn't work that well. Okay. Here it will be, I mean, it will take some minutes. I don't want to waste this minutes on this. Calculating fx is first of all calculating fx at fs but at 0 by definition, and then calculate fx at every other point by the rules, which is derivative of fraction, not very nice. And then do the same for fy, and then for fy we derive by x, for fx we derive by y. We get different results. As far as I remember, I mentioned this example in the morning lecture of the Hebrew students, but uh, just as here, I didn't prove it, just told it from my memory. So hopefully it is what it is. Um, any questions about that? Okay. So go back a little. The derivatives. The derivatives existing, it is very nice. It is not applying that the function is continuous. So there is a gap here between the mysterious notion of differentiability we haven't defined yet, and the derivatives exists. In order to close this gap, we need to understand what the derivative actually means in one variable function, for one variable functions. So my headline is differentiability, but we have to consider some things before we actually define it. Sammy, you good? Any questions? Sammy is not here. She left us. Okay. So differentiability. We need to probe, if that's the right word, what the derivative of one variable function actually means. And we can talk about more than one and more than two things. I want to talk about what's important to me. First of all, intuitively, what does the derivative describe?
The point.
The change in the point is that's really good. To learn physics in school?
The differentiability.
No, many students, their first thought is the slope of the tangent line at the point. So we know I start with that, but the change in the point is something we are going to discuss later on, probably on Sunday. The derivative f tag a is the slope of the tangent line to the graph at the point AFA. The tangent line is FA plus f tag a multiplied by x minus a. What do we get from here? From here, we can go on more than one half. For example, or specifically, 1a, we can talk about geometrically. Geometrically, we have a line. This is tangent to the function. We can generalize. Let's write down. Yeah, probably with one. Yeah, sounds better. Looks better. We can generalize the concept of the tangent line to a tangent, let's say, plane for fxy. I mean, consider, as we've already seen on Sunday, the graphs of functions of two variables are intuitively three-dimensional. So, for example, I can be a graph of such function. And if I look at some point here, it's not only one tangent line, many of them. Actually, it is a plane. Yeah. And even more generally speaking, for f of n variables, it's what you call the thing hyperplane.
Yeah.
Something like that. We cannot imagine it, but we can talk about geometrically and talking about angles and distances and whatever geometry we need to talk about. And tangent hyperplane. Plane is an or like that?
It's cool because y kind of looks like the first two elements in the power series.
Sammy, you are absolutely correct. You've never been more correct before. We will discuss it right now. So geometrically, we can generalize it to a plane or a hyperplane for or of f of x1 to xn. It is interesting, it is known, it is fun, it is useful, it is resourceful, but we are not going to do it here. Our little precious time and our biggie syllabus are not allowing it.
Plane or hyperplane of dimensions of the amount of variables minus one. No?
Exactly. When we talk about the plane, the tangent is line. The plane is of dimensional 2, is two-dimensional, and the line is one-dimensional, which is one less than the plane itself. In the space, yes, the R3, the tangent is a plane, which is one-dimensional, less than the space R3, and so on. We will not do it here. What do we say to the god of hyperplanes? Not today. And B, I can call it analytically. Analytical, that's you write it.
The first one is an I.
First what? No, it's some Y here in analytic.
I think it depends if you're
It's ANY.
N-A.
Oh wait, no.
No.
ANLY. There's a Y after L.
But that's too precision.
No, it's how I write it down. It's this. That's the way. This is the way. Okay. Analytically, Sammy, you said it extremely beautiful. These are the first two elements. The derivative gives us a linear approximation to the function it is fa plus f tag x minus a, which is the Taylor polynomial of order 1 of f around a. And we know that f is approximated by the polynomial. Right here, I want this b is what I want to generalize for more than one variable. I will not do it with generalizing the concept of Taylor series. We will generalize the concept of Taylor series to more than one variable, but we will do it next week. Bezrat Hashem. I just want to write down the concept. And before we do that, I want us to understand how actually good this approximation is. Now we discussed the difference between F and P1, which is R1 by our notations, from the Lagrange point of view. You know, there exists some point C such that R is blah, blah, blah. But as I mentioned, but we didn't write it down explicitly, I want to do it right now. I should think about it for the next years. What I'm going to say now, saying it already in the Taylor part of our course. Well, actually, the last week I should have said it. But I mentioned you the piano is the name of a deceased dude. Approach to the residue, to the remainder, to the R1 or Rn, generally speaking. Piano is talking about the asymptotic aspects of the R, of the remainder. Now, we elaborate. We did not mention it when we discussed Taylor series, and it is a good time now. So now is a good time. The approximation F with P1 is good in the following way. If we look at the limit where x goes to a of f minus P1 above x minus a, it is 0. It goes to x to 0 faster than x minus a, where x goes to a. We denote it with small o. We've already seen small o in computer science somehow. There's the big O, or the bigger function, the small o, when it goes to we go to 0. Yes. But here it is smaller because it goes to 0.
Okay.
No, we can say I want it down with our till. We can say that generally speaking, the limit of f minus Pn above x minus a to the power of n is 0 when x goes to 0. And so, by the usual notations, we can say that f minus Pn, which is the Rn, is the O of x minus a to the power of n. Write it down in different colors. It's not very important for me. Moreover, we can explain what we explain. Why this limit is actually 0. I'm not going to explain the general case, and this explanation I will tillize, put it in teal color as well. But here it's pretty simple. The f minus P1 above x minus a is actually fx minus P1 is that friendly fella above x minus a. We have two summons, or whatever you say. Discussed it earlier. Here, fx minus fa above x minus a minus f tag, which is left after we cancel the x minus a, And we know that when to the arrow of limits, we know that fx minus a above x minus a, as we mentioned earlier, its limit is the derivative f tag a. So we're having here f tag a minus f tag a, which is actually 0. And yet again, it's not very important to me, as I mentioned when we started this subject of multivariable calculus. Mathematical explanations, proofs. I couldn't stop myself. Okay, so write it down, but we don't need time or the will. We need to talk about the technical parts. How do we solve the exercises? So as I mentioned, this is the Peano. So this is Peano's approach. To the remainder of the Taylor or in the Taylor series. We discussed Lagrange approach last week. And as I mentioned, maybe for next week, no, it's not your problem. Maybe should put it inside the syllabus itself, not just as a till note. Yes, till note and different part of the course. Okay, so f is p1 is good in the following way. Now, the differentiability of a function. Now, we define the differentiability of a function. Let's begin with two variables, and then we can discuss more than one variable. Fxy, at the point a, b, the same way. F is called in bold because it's finally the definition itself. Differentiable at the point a, b, if the limit is 0. But what is the limit here? First of all, xy goes to AB. Each point has two coordinates. And secondly, the polynomial of order 1 is actually it's pretty intuitive, but it's the value at the point minus the derivative by x multiplied by x minus a minus the derivative by y multiplied by x y minus b. And as I mentioned, we will discuss next week, probably shortly, but we'll discuss Taylor series of more Taylor expansion of more than one variable. Here the Taylor expansion of a function of two variables of order 1. Derivatives are order 1. It's similar to that. Yes, it's the value at the point, derivative multiplied by x minus. Here you have also y, so it's derivative multiplied by y minus. And what do we take for the denominator? In my words, the limit of what is 0? Of the remainder above some polynomial of 1 degree. So I want to write down here in the denominator something of 1 degree that consider x and y to be the same. Actually, somehow think about the two of them as one. So how we do it, we consider the norm of the difference, which explicitly can be written as that. If this abomination is 0, then the function is differentiable. and if it is not, then it is not. That's the very definition. Now we can write as we did earlier, talking about the derivative of one variable function. We can write denote x minus a to be some h1 and y minus b to be some h2. And we get that the function f is differentiable at the point AB if I write down this limit using the language of h1 and h2. We're having h1 and h2 going to 0. This is the reason I want to write it down with h1 and h2, because our intuition about limits of functions of more than one variable are mainly focused on functions where the limit goes to 0. So x is a plus h1 and y is a plus h2. This is h1. This is h2. This is h1 squared. And this is h2 squared. And of course, I want to show an example where we calculate, where we check if a given function is differentiable at the given point, yes or yay or nay. And then I want to say what differentiability gives us, that it does apply continuity, and what it does more apply or does not. And third thing, which is less important, I want to write it down for the general case, for n elements, n variables, not just 2. Before that, any questions about the gracious limit here?
It's scarce.
As it should be. But after we look for some example, it should be the other way around. So let's start with an example, okay? For example, we check if the function xy is let's take something that we've already calculated its derivatives. We can take the square root or whatever root it was. Something similar was on one of the terms of last semester B. Don't remember exactly what it was or which semester it was, but it was. fxy is differentiable at the point 0, 0. So by definition, we need to check if the following limit is 0, which here we know that A and B are 0, 0. So it is 0, 0, 0, 0, 0, 0, 0, 0. Now that the value at 0, 0 is 0, putting here 0 gives you 0. And we found earlier, something is missing in, missing the A. Earlier that both the derivatives are 0 here for x and for y. So we are left with the following limit. It's only f of h1, h2. And we know what f of h1, h2 is. It is the square root, no square, it's this weird root. It is the fifth root of x cubed, or more precisely, h1 cubed, h2 squared. Now, how do we know that the limit exists and it is 0? How do we know it does not exist? Yeah, we talked about it last lecture. We intuitively consider the degrees of the numerator and denominator. Here we have h cubed multiplied by h squared, which is h to the power of 5, with a root of order 5. So, intuitively speaking, the degree of the numerator is 1. On the other hand, on the denominator, we have something of degree 2, but inside the square root, which is again, intuitively, of degree 1. And when the degree of the numerator is not greater than the degree of the denominator, we know that the limit should not exist. Specifically, it shouldn't be 0. Now, if we want to show that the limit does not exist, we consider two different paths with two different limits, etc. But here it is even simpler. We only need to find one path in which the limit is not 0. So the limit itself will not be 0, and the function will not be differentiable. For example, now we look, for example, at the path where h1 is h2. We get, I mean, if you take the path h1 is 0 or h2 is 0, the numerator will be 0 and the limit is 0 as well, which is not good. I want to disprove the fact that the limit is 0. So our limit becomes the following limit. h1 multiplied by h1 2, it is h1 as well. So in the numerator, it is just, yes, h only should go to 0. h2 is following him. You are correct.
Yes, that one.
What?
On the
Here. Yeah. So it is 2. Here it's just h1. And here it is 2 h1 squared. Now, first of all, the square root of 2, I can put it outside in the denominator. And secondly, I want to be precise, the square root of h1 squared is the absolute value of h1. Now, one can say, you know what, when you come from h1 plus, h1 minus, you get different results. But yet again, we only need to show that the limit is not 0, which is not very hard here. Yes. So, I mean, no, even either. We could just say, you know what? We look at positive h1. Why not? And for positive h1, we have that the limit is h1 above h1. They cancel each other, and we are left with 1 above the square root of 2, which is not 0. So the limit is not 0, and so the function is not differentiable at 0. Any questions about our example?
I mean, it's the same technique you used before, right? But
Yes,
like,
on Sunday.
that doesn't work.
Exactly. The same technique for limits. Sammy, any questions?
Nope.
Okay. Another two things I want to write down, then we can finish. First of all, mind the theorem. about differentiability. On one hand, if the partial derivatives are all continuous at the point, then the function is differentiable there. It's not true for the other way around. I mean, function can be differentiable. The limit is 0, but one or more of the partial derivatives is not continuous at the specific point we look at. What does it mean? Technically speaking, it means that our elementary functions are all differentiable because all the derivatives, x squared, y third, etc., are continuous. And every theorem from now on, considering Taylor or whatever we're going to see in the last 2 weeks of the semester, that is requiring differentiability, we know that our elementary functions, polynomials, exponentials, etc., are differentiable for that. On the other hand, if the function is differentiable, then it is continuous, and the partial derivatives are not necessarily continuous, as we mentioned, but do exist. So this, it's rain or so wind? Ah, shit, I think
Both.
my umbrella. Yeah, fine. So differentiability by this notion is what generalized differentiability from functions of one variable. Any questions about the theorem? Yet again, not proving it nor explaining. We should know it. That's all.
It exists, okay.
Yeah, I mean, if they don't exist, so we cannot write down, right? They do appear here in the numerator. It's not that simple. I mean, one can define differentiability without explicitly talking about the partial derivative, and then you know what? It should be partial derivative, like some kind of corollary, but it's not how we do it here. The last thing I wanted to talk about, let's write it over here. Generally, general if we denote the vector of all partial derivatives, we will discuss the vector later on with the following nice notation. It's called nabla. It's an upside down triangle, which is a triangle of FA, and we denote with age the vector of many ages. The limit or the condition, the requirement of differentiability is actually the following. This is the case, the general, read it down explicitly for 2 variables. But considering it's now n variables, age goes to 0. This is f of a plus age minus f of a. Here it is the norm of age, square root of the sum of the squares. And the first derivative multiplied by the first age. The second derivative multiplied by the second age. This is the standard inner product. So generally speaking, for n variables, we have here this vector of the partial derivatives, which is called gradients, by the way. We'll talk about it, as I mentioned, next week, multiplied by age. And again, when it is written in the vector way, it looks more elegant. it is hiding behind the age and a lot of variables.
A lot of programs for future us.
No. Most, as I mentioned, most of the examples, the questions in the exams are about two variables, some of them about three. And yet again, when we discuss more than two or three, it's actually pretty easy, as we did here, for example, for example. Okay, Sammy, any questions before we close the Zoom and go each to his own path?
No. I'm
No.
good.
Okay, so you do you. We meet again on Sunday.
Okay.
Bye
Bye.
bye.